Welcome back, everybody. Here we are again. This is the third recorded lecture for week 2. And in this short recording, we're going to talk about how to compute perfect Bayesian equilibria in an extensive form game. And the difference with the previous recording is that here we're going to also compute perfect Bayesian equilibria for general mixed behavioral strategies. So strategies where you also allow players to randomize over their actions in information sets. So here's an extensive form game. It's a two-player game, and it starts at the top of the diagram with a C for chance. And as you can see, the game starts with this chance move, which moves to the left with probability 2 out of 3, and to the right with probability 1/3. So player 1 observes which way we went, to the left or to the right. And depending on that, he can either choose to enter the game, and the payoffs are given, right? So on the left-hand side of the diagram, the payoffs are 2 for both players. On the right-hand side, player 1 gets 2 and player 2 gets 8. Or he can decide to continue the game, in which case the move goes to player 2. So player 2 can observe that the game continues, of course, but he does not know whether we are on the left-hand side or the right-hand side of the diagram. So he has to make a choice between the left or the right strategy without knowing which side of the diagram he is. So this is a game that you can think of as a kind of a special case of a cycling game, 2x2, that we looked at in with the special feature that on one side of the diagram, the game simply ends. So it's, you could say, a simple form of a cycling game. So this is the game we're going to analyze, and we're going to look at, well, maybe I can go to the next slide already. We're going to look at perfect Bayesian equilibria, and also it allowing for mixed behavioral strategies, which means that a player can, in each node, can choose, or each information set can choose to randomize between his actions. So for example, let's go through that for a second. So player 1 needs to make a decision here, and he can choose to go this way or that way. And of course, you can just say, well, you have to choose one of the two, but we also allow him to choose to go down with a certain probability P, and to go to the left with the remaining probability 1 minus P. In the same way, on the right-hand side, we've got Q and 1 minus Q. And also in the same way over here, in this information set, so this is a non-singleton information set, but you can do the same over here. And so you can, there's a choice between left and right for player 2. And yeah, he's allowed to choose left with a certain probability. That's called Z over here. But of course, because this is an information set, that means that if here he would make a choice to play this with the probability 1 out of 19, right? So that's one of the options that he now has. Then he, of course, is also required to use the same probability over here, because you can't see the difference. You cannot condition your actions on things you don't know. So that is the restriction, that this number over here is the same as over there. Yeah, and for the rest, there is this belief alpha. So in each information set, non-singleton information set, players need to have beliefs if you want to compute perfect Bayesian equilibria. So this is the only non-singleton information set that is currently present in this game. So we only have one probability to specify, namely the alpha, and to be in this node over here. And then 1 minus alpha is the remaining probability to be in this node over there. So that means that an assessment, so that is a profile of strategies together with a profile of beliefs in this game, boils down to a specification of these 4 probabilities, P, Q, Z, and alpha. So we'll keep things simple and just identify the entire assessment, which is basically something in, what is it, R8 with these 4 numbers, just to keep the notation short. Yeah. Okay, so what are we going to do now? We are going to check for each of such a specification whether or not it represents a perfect Bayesian equilibrium. Okay, so how do we do that? Well, there are several ways, but usually the at least in games that look like this. Of course, it depends a bit on the game tree that you are currently facing. And if it's a complicated game tree, then these computations might be complicated. But here we start with the belief alpha 1 minus alpha, and we're going to check sequential rationality. So we have sequential rationality dictating that given this belief, a player should play a best response. Well, there's not much of a best response going on here. So there's this player 2 that needs to make a decision here, but he is the last player to take an action over there. Meaning that once he took that action, the game is over. There's nobody that decides something after him. So the only thing that best responses are going to do is to say that you maximize your payoff or expected payoff with respect to alpha. What is then that expected payoff? Well, that's something you can compute, right? So you can check now when, given this belief, going to the left is better than going to the right. And if you move to the left, over here and over there, of course, then what is your expected payoff? Well, with probability alpha, you are over here in this node. And if then you move to the left, you get 1. So going to the left gives you expected payoff of alpha times 1. Plus, well, with probability 1 minus alpha, you're in the other node. And if you then move to the left, your payoff is 2. Like that. And that should be bigger or equal than, well, what happens if you move to the right. And if you move to the right with probability alpha, you get 2 over here. And with probability 1 minus alpha, you get 1. So that's how you compute this. And of course, if you figure this out, it means that I think alpha should be smaller or equal to, okay, actually compute it, right? So on the left-hand side, it says 2 minus alpha. And here it says 1 plus alpha. So indeed, you get that alpha should be at most a half, which makes sense, right? So the payoffs are symmetric. So this is what you would expect, but you can also compute it. And of course, if the numbers here are not that nice and symmetric, you can still do these calculations and see what the condition will be. Okay. So this is the calculation. And based on that, we will consider 3 cases, namely if alpha is really smaller than a half. So that means that player 2 will actually uniquely choose left. If alpha is strictly larger than a half, in which case player 2 will strictly uniquely choose right as a best response. You got one best response in both these cases. Or when alpha is exactly equal to a half, and that's a bit more complicated because then player 2 is indifferent, so he can still choose everything, and then we need to analyze further. But the first two cases are easy because you know what player 2 is going to do in this information set, and then you can infer what player 1 will do. So we'll do one of those and do the alpha is a half case here. The rest of the details you can read in the reader. So let's see. If alpha is strictly smaller than a half, then from sequential rationality, what we just computed, we know that player 1 will uniquely select left. And he's only got one best response, which is to choose left, which means that Z is equal to 1. So what will happen next? We've got player 2 moving to the left over here and over here. And now you can perform a kind of backwards induction. So you can go to the previous decision nodes. So for example, here on the left-hand side, if player 1 is here, given now the strategy of player 2, what can player 1 do? Well, he can move to the left and get 2 over here, or he can move downwards over there, and then he will get 3. So his best response is to choose P is equal to 1. And in the same way, you can verify what will happen here. If player 1 moves over here, he gets 2. And he moves, if he moves downwards, we go here and he gets 3. So also Q will be 1. That's not sequential rationality. Yeah, maybe sequential rationality, right, is playing best responses. So that's part of sequential rationality. And yeah, so now what you can do is actually compute, because we're not done yet. You might think, okay, now we know everything. Now we know that player 1 goes here. And player 2 moves over here. So you might think, okay, now we got everything. But in some sense, now we have to close the loop. We know the Z, and we know P and Q, but we still now can compute alpha, because there is also now consistency. Consistency says that alpha should be given by Bayesian updating, right? And how does that work? Well, now we can, this information set now is reached with probability strictly larger than 0. It's even 1. So we go to we start here and then we move to the left with probability 2/3, and then we go down. So we've got a probability 2 out of 3 to end up here. And yeah, so we move here with probability 1/3 and down here with probability 1. So we have a probability of 1/3 to be in this node over here. So now you can compute the alpha. The alpha should then be the probability to be in the node on the left-hand side divided by the total probability of being in this information set in the first place. So that would be 2/3 plus 1/3. Yeah, in this case, the denominator is 1, of course, so this is easy, and then alpha will be 2/3, which is actually larger than half. So you see that we don't find any perfect Bayesian equilibria in this case. So there are no perfect Bayesian equilibria where alpha is smaller than half. That's what we conclude now. As a little aside, yeah, so here I found that the alpha is actually equal to the true probability, but you could imagine that over here you would have, for example, maybe a different color to make it clear, a half, and let's say here 2/3, 1/3. That could be, right? So then you can still compute the alpha, because the alpha will then be, well, the probability of ending up in this node over here, which is 2/3 multiplied by a half, divided by the total probability of being in this information set, which is the probability of being over here, which is what we already computed, added the probability of being over here, which is now 1/3 times 1/3. And yeah, you can compute that, right? So let's multiply by, what do we multiply this by? 18, I guess. And if we do that, we get 6 in the numerator, I guess. Is that correct? Yes. And so this is also 6, and that will be 2. So 6 out of 8, which is 3/4. So we see also if this probability of being in the information set is, it's not 1, right? So it can be smaller, strictly smaller than 1. But as long as it's positive, you can actually always use consistency, and then it pins down the alpha, right? So the alpha is then uniquely determined. But okay, so in this case that we are currently looking at, the conclusion is simply that for alpha smaller than half, we haven't got any perfect Bayesian equilibria. So we're going now to cover the case where alpha is a half. Sequential rationality in this information set of player 2 says that then player 2 is indifferent, so any z is fine, right? So everything is a best response, so that does not really pin down anything. But what we are going to do now is then to look at the cases. We split the 2 cases, namely when the probability of the information set being reached is 0 over here, right? And the case when it is larger than 0. So these are split. So you see, you get a kind of subdivision in different cases here. And what does it mean that the probability is 0? Well, that means that P should be 0 and Q should be 0. So this information set is not reached, and that means that consistency cannot be applied, right? So now the probability here is 0, so you can't use Bayes' rule. So what does that mean? It means that player 2 can choose any z that he cares to take. The only thing that you need to check now is whether sequential rationality is respected. And for player 2, we already know that that is fine, right? Because he's completely indifferent. But there is still something to check for player 1. Because player 1, we say, is choosing to move over here. And on the right-hand side of the diagram, he moves over there. And that should be his best response. So when is that the best response? Well, let's say call this A and let's call this B. So player 1 strictly prefer to choose A over B. If what? Well, if 2 is at least as large as what he gets if he moves down here. And what does he get if he moves down here? Well, with probability Z, we go over here and he gets 3. And with probability 1 minus Z, we move over here and he gets 0. So 2 should be at least as large as 3 times Z plus 0 times 1 minus Z. That's what sequential rationality dictates. In other words, Z should not exceed 2/3. And yeah, you can do the same analysis on the right-hand side, but you will see that that will give you exactly the same because the payoffs are the same. So this is the only condition that you get from that sequential rationality check. And that means that any of these choices is a perfect Bayesian equilibrium. So if you choose P and Q equal to 0 and Z at most 2/3 and alpha is a half, then any of these choices constitutes a perfect Bayesian equilibrium. And you can continue like that. So you can also check when P and Q are not equal to 0 and they are bigger to 0, and you'll find a few more. So all that is done in the reader, so you can read that for yourself. But I will stop here and just close this session with saying that if you do that correctly, these are all the perfect Bayesian equilibria that you find in this game. So there are actually 3 line segments that are connected to each other. So I'll stop here and I'll see you again in the next recording, which will be about the same game, but then we're going to do a refinement of a refinement, namely sequential equilibrium, which is a refinement of the perfect Bayesian equilibria that we found here. So see you there.